What's up? How's everyone doing? Good to see you here. Ali, Lachey, Kenneth, Timothy, Blake, Lachey, Ivana, and Timothy. Kenneth, during class, I was going to take this class in my room since I have 2 monitors from the library. Oh no, shout outs to library people. Hopefully, yeah, everyone's doing well out over there in the library. Good stuff going on. Caden, good to see you here. Let's throw some 5,000 points if you're here. Say hey in the chat. Remember, you only get points if you talk. So let's throw some points. I'm already friends with you on Pokemon Go, so I couldn't say, oh, that's all right. No, that's all right. 5,000 points. Drop some points right here. Got all the... Why does that one look different? Cool. Trying to think my buttons right there. Okay, let's go grab the homework. We're going to work through the homework step by step by step. And so let's go over here to the homework. And then we'll work through the quiz. We're going to do every homework question, starting from the very beginning. A very good place to start. So, here we go. 323. Statue 1, chapter 14, homework. Q1, okay. Chapter 14, homework, question 1. Question 1. Oh, wrong one. Wrong one. There we go. Bring this up right here. Close that chat. Awesome, Kenneth, right there. Send it to me. Let me copy that down, Kenneth, real quick. There you go. There you go, right there. All right, cool, cool. Okay, let's head over right here to the homework. Let's do it. A food company sells salmon to customers. So they're telling you right now that the average weight of a salmon is 40 pounds. So I want you to pretend you're seeing this right now. I want you to pretend. Nice job, Kenneth, right there. So I want you to pretend that you are about to order for your restaurant salmon. How many salmon do they ship you? So how many salmon are they going to ship you in a box to your restaurant? How many salmon are they going to ship you in a box? How many of these salmon are they going to ship you in a box? Try going through the MyPearson website. Try the MyPearson website. How many salmon are they going to ship you in a box? Yours might be different than mine. So yours might be different. The carton is 36. The box right here is 4. Does that make sense? So they're going to ship us 4 salmon. So when we do this right here, let's look at the mathematics behind this. For the mathematics of this, let's go here to the review sheet. You ready? We are talking about the weight of a salmon. Does that make sense? Is that quantitative or categorical? You're going to hear a lot of the same answers because we're working on chapter 14 right now. Is the weight of a salmon categorical or quantitative? Is the weight of a salmon categorical or quantitative? It's quantitative. Great job, Lachey, right there. It's quantitative. So we already have this copy right here. Let's take another screenshot of it. We're just going to take this right here and let's only take the quantitative because that's all we're going to be using. And so we need to identify for this question. We need to identify for this question the following. What do we need to identify? To solve this question, no matter what it asks, we would need to find what? What should we try to find? What values, because it really comes down to knowing your notation, what values, and great job, Isabella, Julian, Jackson, Kaylin right there. Sample size, great job right there. So the sample size it uses are n equal to 4, so that's the first sample size. The next sample size is 36. And the next sample size is 121. That's just subscript right there for the first, the second, and the third sample size for the first, second, and third question, respectively. But also we need to know what. So we just found all the sample sizes it uses. We also need to find what. What other notation is there currently on the screen? What else can you find? What else can you find? Sigma. Sigma is going to be very important for this. So it says the standard deviation of these salmon is 4 pounds. 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 4 poun There is an additional thing. We don't need it for this question. There is 40 right there, which is mu. So think about this. So mu y bar would be the expected mean. So if you work at a restaurant and they send you 4 salmon, what would you expect the average weight of those 4 salmon to be? You understand? Does that make sense? If they send you 4 salmon to your restaurant, they say, here's a box of 4 salmon. What would you expect the average weight of those salmon to be? 40 pounds. That's what that stands for. It says the truth is 40. So your sample mean would be expected. That's your sample mean, the expected sample mean. So the expected sample mean is 40 because the truth is 40. So you're saying, well, if the salmon weigh 40 pounds and I get 4 of them, then my average weight of the salmon should be 40 pounds. Close to. Does that make sense? So that's what that reads. The expected sample mean is 40. The standard deviation of the sample mean is equal to sigma over square root of n. Now, what are you going to notice about this question? As n gets larger, the standard deviation will get water. As n gets larger, the standard deviation will get water. The standard deviation will get water. It will get smaller. So when you do this question right here, it goes in order from larger and larger sample sizes. So we take the original sigma equal to 4, and we do 4 divided by square root of 4, and that's the first one. 4 divided by square root of 36, and 4 divided by square root of 121. These are all perfect squares, so they're really nice. I think they always use perfect squares. So mathematically, those would be equal to 4 divided by 2, which is equal to 2 for the first answer, 4 divided by 4, which is equal to 1, and this is 4 divided by 11, right, which is not a pretty number. 4 11ths, that's a repeating one, isn't it? 0.9090909, so times 3. I don't know what that is repeating. 0.363636. That's a guess. But, wow. When you learn too many fractions. Wow. Okay. I've learned too many fractions, apparently. Okay. Didn't expect to know that one. Okay. The first standard deviation we calculated was 2 right there. Apparently. Oops, didn't mean to learn that many fractions. The next standard deviation we calculated was 1. Oh, wait. See, now I'm going to get them wrong. 4 divided by square root of 4. 4 divided by square root of, cartons. The standard deviation is 4. Oh my gosh. No. Okay, someone yell at me. Wow. I did the hard one, but I couldn't do the easy one. Correct Brian's math for 5,000 points. You should use your calculator to check your work. Correct Brian's math for 5,000 points. No one yelled at me for the easy one that I got wrong. Correct Brian's math. Great job, Juliana, right there. Brian got it wrong. 6 times 6 is 36. So I did the tough one. I did some tougher mathematics. So that should be 0.67. So that was incorrect right there. 16, which I think I had in the previous version of this. So my brain was still kind of booting up from the previous version we did earlier today, where it did use 16. We might have deleted that one, but check out earlier office hours where I think it was 16. And my brain was thinking about that. And I was also like, it's so nice. It's 4 over 4, but it's not. It should be that for the second one, 0.67. So just make sure to do your math properly. It's easy to make mistakes. Check your work and put it into the calculator by doing things like 36 and taking the square root of 36 is equal to 6. I know it sounds obvious, but we do make mistakes. So the last one was 0.3636, and we did check it, but do round properly. If you make an error on the rounding, just let me know. So there we go, and great job, Meredith, right there. Excellent work. We all make mistakes. It's quite possible. The distribution of the sampling weights turns out to be skewed to the high end. Would the distribution of sampling weights be better characterized by a normal model for the boxes or the pallets? So the boxes are only for 4. What condition from today's class is it talking about right here that we would need to know if it's skewed? Pallets, because it has a larger sample size, right? So the third condition right here is the large enough sample size that we talked about a lot today in class, that if we have skew to the distribution, if it's skewed, we need a larger sample size. So the more skewed it is, the larger the sample size is needed for quantitative distributions. So it's going to be more normal for the palette. The palette has 121. So the palette says, and it's not regardless of the underlying. Nope. The palette, that is totally wrong, because as long as the underlying distribution is normal, here it is. This one is, wow. The palette, because regardless of the underlying distribution, the sampling distribution of the mean approaches the normal model as sample size increases. And that's what we saw a lot today, that I thought it said regardless, it's normal. No. As the sample size increases, the distribution becomes more normal. And that's one of the two things in the what. That's one of the two things of the what, that it becomes more normal as n increases. That's one of the two things in the what. It becomes more normal as n increases. The central limit theorem. So the central limit theorem states that as n increases, it will become more normal. And we saw that right here. And that's also part of the large enough n condition that we check for condition 3 right here. We see if it's skewed or normal, and then the more skewed it is, the larger n we need to have an approximately normal distribution. Good stuff. Oh, that's it? Well, that's question 1. Woo! Question 1 done. Everyone ready? We can probably get this done in about 30, 40 minutes. Everyone get a question? Can you do a waiter waitress? We are, yep. We'll be doing that waiter waitress one, you bet. We're going to do this all in order right here, Isabella, so stay tuned, and we will do the waiter waitress question, you bet. That one's a tough one. That is a tough question. So here is question 2. Let's check it out. You got it. No worries. No worries. I appreciate it. Isabella, let me throw you some big points right there. Thank you for asking, Isabella. Remember, hang out, get these points, and we're just throwing some crazy points. Make sure to stay around for test 3 as we start doing those materials. But thank you for asking. Here we are with the second question. A standardized test for graduate schools has a mean score. Instantaneously, you're thinking, this is what kind of data? It has a mean score of this. This is what kind of data? What should you think of instantaneously when it says it has a mean score? Quantitative, exactly. You should be like, okay, if I go to my formula sheet, and this is what we're going to be doing a lot right here, we want to practice on how to solve these. It's not just about solving them, it's how do we solve them. We go, okay, it's quantitative, so we're going to grab this right here, drop it in, and we're going to use that to solve the questions. Let's go grab the question itself right here and start marking our what. What's the next step we're going to do to solve all of these? We're not even going to read the question yet. The next step is to do what once you know it's quantitative. What is Brian going to do right here? And so follow along with me. This is how to solve these. It's all about that.
Notation, brother.
Notation, brother. Thank you, Leo. We got to do that notation. Mark the notations. A standardized test has a score of this. What did they just tell you? It has this score. What did they just tell you? It has this score. That is the score on the test. That is the average score. That is the true mean, which is mu right there. That is mu. So what is this over here? The other quantity mean, mu is equal to this. If you were to talk to students, what would you expect to see? So I'm actually talking about this currently. If you talk to like 50 students, what would you expect to see? So think about what that means. Like you go out and talk to 50 students and you ask them what they score on the exam, you'd expect to see what? So that says expected sample mean. That's how that reads, expected sample mean. So what would be you'd expect to see 147, right? It's like, well, I mean, if the average is this and I talk to 50 students, I'd expect them to have an average kind of close to that. But there will be variation in what the 50 students do. So now we need to look at the rest of the notation. The standard deviation is this. What quantity is this? And this is usually where mistakes are made. This is usually where mistakes are made. What quantity is that? That is the standard deviation. That is sigma. Great job, Kaylin, right there. That is sigma. So that quantity is sigma. And so make sure that is not just the standard deviation of a sample. That is the true standard deviation. True, and great job, Ali, right there. We got through some more points in the chat. That is the true standard deviation. So now we're probably going to see in here somewhere a sample size. I'm guessing as this question continues, we'll probably see some sort of sample size discussion. It's also unimodal and symmetric. Oh, whoa. What are they telling you right here with unimodal symmetric? Unimodal and symmetric, they're telling you what? They're telling you what with unimodal symmetric. So that's some really big stuff. They're basically saying normal, right? So it looks like we're probably going to pass the nearly normal condition. So they're saying it's pretty normal. So that's some good info right there. A test preparer organizes, teaches small classes of 4 students. So the 4 is now their what? The 4 is now their what? That's the last bit of notation we need. Yep. And we are probably going to meet the large enough n because if it's normal, n is 1 is large enough because it's originally normal, so we should be good. Okay, a larger, okay, so there's the larger. So there's a difference. So they're doing 2 sample sizes. So this is just another group right there. It's just the first time you do it and the second time, 49. And they're using perfect squares. Thank you. So those are just 2 different distributions. Both organizations publish the mean scores of their class, complete parts A through C. Okay. What would you expect the sampling distribution of the means to be for each organization? So solve the equation for both. What would you expect the mean to be for both? It's asking you currently about this quantity. What would you expect the mean to be for both of them? Use the information on the screen. Don't look at their answers. What would you expect the mean to be for both classes? What would you expect the mean to be for both classes? 147. Does that make sense? Because it's just the expected mean of both samples is equal to 147, and we expect it to just be that. There's no other thing in the formula other than the expected mean. Great job, Ali and Sullivan right there. So both distributions will be approximately normal with a mean of that. That looks good right there. That should be good, yes. Now, if either organization has a graduating class with a mean of 158, they'll take out a full paid ad in the local newspaper. Okay, so which of these would have more variation in it? Which class has more variation in it? Which one would you expect to have more variation in it? The larger class or the smaller class? And we can find the answer over here mathematically. Which class would have more variation in it? The smaller sample size. The smaller, because you're dividing by a smaller n. Because as the sample size gets larger, and I think we have the central limit theorem still up, as the sample size gets larger, so here's the normal distribution, and here's the small class with like 2 students in it, there's less variation. But if you go to a larger sample size of like 25, there's even less variation because you're dividing by a larger number on the bottom, square root of n. So the larger class would have less variation in it. I mean, imagine this. If you only have 4 students and one of them is an absolute genius, what is that one student going to do to the mean? If you have one student who's an absolute genius out of the 4, and then what is that one student going to do to the mean of 4 students? If one student's like, it's going to skew it, right? But if there's one student who's a genius out of the 49, what's that going to do to the 49? I mean, it's still going to impact it, but one student averaging with the 49 is going to have less of an impact. You're probably going to see something a lot closer to the average with the 49 students, where with the 4, there could be more volatility to it because there's more variation. So that's what they're getting at with this question. Let's see how they answer it. A mean score of 158 is, oh, they're doing z-scores. Okay. So we actually have to find the standard deviations. It is more likely that the small organization will have that success. We know that. So we have to find the new standard deviation. So let's go here and find it. The original standard deviation is 11. Divide by the square root of 4. So that's 2. That should be 5.5. Please check my work. So that's the standard deviation for organization small. The standard deviation for organization small for the sample mean is equal to this. The standard deviation for the large one is going to be standard deviation organization large. That's just a subscript there for large. Is equal to 11 divided by square root of 49, which is 7, one of my favorite squares. I used to write on bus 49, so it's one of my favorite numbers growing up. And that should be 4/7. 7th is 0.4, so it should be close to about, my brain, 1.156. That's probably off. 11 divided by 7, 1.156. 1.157, close enough, but we should write them as 1.15714. Check my work. So now it says the observed mean that we want to understand, this is a tough question, is this. It says if they have above a 158, was it? So try to solve this out. 158. So what do we have to do? What is going to be the formula? And we're using this right here to solve it. This is like the balcony question. Who here can solve the first one? Ooh, is the first one exactly? Who can solve the first one right here? So now we need to solve out. We need to go y bar, which is the sample mean, minus mu, y bar technically. And then we need to divide by the standard deviation of its respective one, which is the small. So that it's basically actual minus observed. So we're saying if they actually get a 158 and they're expected to get a 147, how unusual would this be? How far away is 158 from 147 in terms of standard deviations? And I think that's 2. Is that 2? They'd be 2 standard deviations above the mean. Where in the bottom one, it's the same formula. So it's the same formula. We're just going here, y bar minus the expected sample mean over the standard deviation of the large. And there it is right there. So we would do 158 minus, and then, 147. Still the same difference. But then we divide by the standard deviation, which is 1.5714. I'm going to do this one right here. How do I keep clicking that button? So now we take this number right here and do 158 minus. So that'd be 7 standard deviations. 7, I guess because it's 11. Yeah, we could have just mathed it out. 7 standard deviations. So that'd be very unusual. A mean score is 2 standard deviations above the mean for the smaller one and 7 for the larger. So that is very unusual for the large class. Now we got to do 137. So both organizations advertise that if any class has an average below this, they'll pay for everyone to retake the test. Which organization is more likely to pay? See you, Kaylin. Good work right here. The smaller one is going to be more likely to pay. Once again, they have more variation in it. So what do we need to do right here? How are we going to change what the mathematics we just did to solve this next one? To solve this next one, what will we change about the mathematics? Because we already know the standard deviations. So what are we going to change about this to solve the next one? So we're going to do the same sort of work, right? Because we're just finding out how unusual it is. I think it's 137. So what are we going to do right here? 137 minus 147 over 5.5, whatever that equals to. And 137 minus 147, same difference up top, which is negative 10, over 1.5714. And that is equal to the value there. So let's see, that's 10 divided by those values. So 11 divided by 7, negative, or 10 divided by that is equal to 6.36. And negative, technically. Subtract the what we saw from what we would expect. So this is what you see in a sample. I'll highlight that as I say it. This is what you might see in a sample. And then this is the expected truth right there, because that's what we expect to see. And that's what we're saying we might see in a sample. So that'd be sample mean minus expected to see how far it is away. And so this one right here is negative, and it's 10 divided by that. 10 divided by 5.5 is 1.18. That's 2. There we go. And I think those round properly right there. Any questions on this? Wait, how do we get 158? The question tells us that if they have that score, like if we saw that in a sample, so they're saying if this were to occur in a sample. So it's saying a hypothetical sample right there, and this is saying another hypothetical possibility. Like, what if this were to occur? Does that make sense? And it's saying below, so we don't have to add the negative before it. Does that make sense, Ivana, right there? How does that look? No worries. Thank you for asking. Please ask those questions. This is a tougher problem. It's got a lot of steps. What is the number one thing? Say it one more time for 5,000 points. What does this question boil down to? This question has repeatedly boiled down to knowing what? This question has repeatedly boiled down to knowing what? This, like, the whole thing of this question has boiled down to knowing the notation. So great job right there, Meredith. You have to know the notation. So 1.82, and please practice these steps, understand the notation, and then it was 6.36. Hopefully we carried all the math correctly. Woo! I'll tell you, even I get a little bit afraid. Even I hold my breath on these questions to say, oh my gosh, oh my gosh, oh my golly. We get one thing wrong, and just everything explodes. So that was a pretty tough question. Like if you can get that question right repeatedly and know how to do the steps and know the notation, that's a lot of the chapter. Oh my gosh, that's a tough one. Oh, wait, is this a variation on the waiter waitress question, or did they change it this semester? Might change the waiter waitress question. This is a waiter waitress question, but with a different theme to it. Period, though, was able to go through, remember the steps. Nice job. Yeah, great. Oh, great job, Allie. Congratulations. These are tough. It boils down to, I said it's first day. I said, figure out this is how much you get tipped. Is how much you get tipped quantitative or categorical? So first thing you look at this and you say, how much am I getting tipped? Is that a quantity or a category? You got this. Yeah, thank you, Allie. So you look at this, you say, is this quantitative or categorical? How much am I getting tipped? How much am I getting tipped? It's quantitative. So once we read this in a question and we see things about the sampling distribution, like it's talking about the sampling distribution somewhere in here, believes that the distribution of his tips, like what do you get from a sample, or this is not a sampling distribution yet, has a skew to the right with a mean of this and a standard deviation of this. What two quantities did this person just find by saying they believe their tips have this right here, have a mean of this and a standard deviation of this? What two quantities did they just find? Mu and sigma, Allie, great job, Allie. We're just going to keep throwing out some mega points right here because that is exactly, and great job, Sullivan, right there. They just found mu and sigma, so we know the mu, we know the sigma. So the mu is, well, that's the sigma. There's the sigma and this right here. But it's not normal yet. It's slightly skewed. So what sample size would you suggest to them was slightly skewed to the right? What sample size? That's condition 3 right there. What sample size would you suggest? We're just doing all this practice right here. You'd say you need a sample size of at least what for it to be nearly normal? 25. Your sample size is large enough. Great practice and good job there, Sullivan. This is the big thing. Look how we're practicing a lot of different things like our conditions. Randomly take your samples and then make sure it's less than 10% of all, which it pretty much has to be. In great job, Lachey, right there. And then we would need a sample size of at least 25. We want to think about these questions and what could be asked and what information we're getting right here and boil this down to everything we need to know. Here's the mean, here's the standard deviation, and here's the shape of the original distribution. So let's take a look right here. The first question asked, explain why you cannot determine the probability that a party will give him a tip of 20. So I think they're getting to that. So the distribution is skewed because it is non-symmetric and does not meet the conditions for the normal models. So the probabilities of values with this distribution, that sounds right. That sounds it. Is that it? That's it. Yeah. So yeah, we need to, can you estimate the probability the next 4 parties? Probably not large enough. It says slightly skewed. My Pearson, you better not. Oof, we said 25. Are they seriously going to do it with 10? My Pearson is tricky, and that's why I'm glad we do these. My Pearson needs to put 25 here. The book and some of these questions update. And I think some of the people who write these questions, I want to complain about Pearson, especially this semester. The book, the slides, and the everything are meant to all coincide. And that's why I give points back. But I think what they're going towards right here is that at some point, n is what? At some point, n is what? Use the words on the screen. So it was slightly skewed. Little bit of skew. So they're in between the 1 and the 25. Little tiny bit of skew. At some point, n is large enough. Exactly, Ali. At some point, n is large enough that we pass this condition. So if it's 1, it doesn't pass. If it's 4, it doesn't pass. If it's 10, because it is a gradient inside of here. Like, what if it's super duper skewed? I'm going to ask something outside the bounds of this. What if it's super duper ridiculously skewed? How large should n be? If it's super duper ridiculously insanely skewed like we've never seen before, how large should n be? According to these rules, 100, yes. But let's say it's super duper ridiculously insanely skewed more than anything's ever been skewed. Super duper skewed. Imagine my Pearson saying super duper. I love that. What if it's super duper crazy skewed? Yeah, 1,000, maybe something like that. So these are just the bounds by which, like, literally they come from the book. Yeah, and it's the more skewed it is, the larger n needs to be. 100 works for pretty much anything. 25 is good for most skew, but they're going, when you go theoretical, it's hard to say exactly, like, at what point is it normal? It actually technically never is perfectly normal. It just becomes less and less skewed. And then people even say the normal curve doesn't even exist when you think about it. Math theory is fun. So anyways, I think they're going for, with this answer, it's going to be normal enough. So let's take a look. Is it likely that his 10 parties today will tip an average of at least 15? Okay. Did they ruin the really good waiter waitress question and turn it into this one that I don't like nearly as much? Okay. So what should we calculate for 10? What should we calculate for 10? 10 is the sample size. So what should we calculate for 10? They want to know tip $15. We should calculate the standard deviation because the mean is the mean. And the standard deviation will be sigma over square root of n. So 5.4. Square root of 10, I don't know that one. It's like 3.1. It's close to it. Square root of 10. Boop. 3.16. 5.40. There we go. 1 point. That's square root of 2, basically. That's interesting. Basically. Bingo, exactly. There's still, yeah, good. I love that other one, Morgan. It's a good question. Good to see you, Morgan. So there's the standard deviation, and now we need to figure out how unusual $15 is away. That's pretty unusual. It's pretty unusual. If you already look at it a little bit, it's gonna be like 3 standard deviations or something. So pretty unusual. So 15, I'll write the formula below that I'm using. Let me zoom out a little bit and also disappear so you can see it all on the screen at the same time. Okay, so we take we're going to take y bar minus mu y bar over standard deviation of y bar. We calculated the standard deviation of y bar here, and mu y bar is equal to mu, so mu y bar equals to mu, which is equal to 9.60. So there's the quantities we need. So the sample mean being 15, the expected mean of what we would expect to make, 9.60, over the standard deviation of 1.70 to get the z-score. It's the whole point of finding this. And let's find that quantity. So how many standard deviations above the mean are we? We are a total of, it's going to be 3 exactly, or close to, no, 3.16. It is pretty unusual. That would be pretty unusual to make $15. It's more than 3 standard deviations away. A sample of 10 parties is large enough. Well, 10 may not be large enough to use a normal distribution. It is likely that the sample average is starting to approach a normal distribution. The standard deviation of this distribution is no. Oh, there it is. Look, you see the number right here? Remember that number we just calculated? Oh, I kind of like this answer. While I think this is it. While a sample of 10 parties may not be large enough to use a normal model, which is what I was kind of getting at. Didn't like large enough. Oh, it didn't? Oh, it didn't. Yeah, I like this right here. This right here, and it does give the quantity. So, Ali, thank you so much for already checking. I kind of liked this answer where I was like, remember how I was like, eee. So they are kind of getting at it. Don't ban this question, Evan and Blake, don't ban this question. While a sample size of 10 parties may not be large enough, which remember our conditions right here, we said we kind of need 25. The distribution of the sample mean is equal to this. It's more than 3 standard deviations, which is what we calculated, and that should be correct. No, ban this chapter, Kenneth. That was a really good answer. Once again, please notice this. I didn't read any of the answers. And what was I doing? I didn't like that we were here at 10. Do you remember how before even reading those answers, because this is a new question for me, we were here at 10, so I was like, I was questioning it. Remember that? I was like, eee. I was like, 10 is, I don't know. Like, I'm a little iffy on that, right? And then I went ahead and calculated. I calculated the quantities, which we got 3.1 right here. I went ahead and calculated the z-score, and then went ahead and calculated the standard deviation. So if you're seeing these answers, you can probably get the question right, but the real learning takes place. The real learning of this question takes place by solving it and knowing the notation. So I beg of you this, if you're working these problems with us right now, sit down and mark all the what in every problem you do. Every problem you do, be able to mark all the what. The real learning takes place when you start doing this and can solve the formulas, and it all begins with knowing the what. We're about to do the next problem here. Know that notation, brother. So know the notation, and this is where the real learning takes place to make sure you understand the chapter, because I know I probably give away some answers, but we're here to learn, and I appreciate it. Even if you just get the questions right, that's good, but practice and learn. So let's do the next question. We're here about that positivity. It is the real waiter and waitress question. We need some like scary music right here. Oh my gosh. Oh my gosh. The real waiter waitress question. The real one. The
scary question. The one that everyone says, how in the world do we do this question? There's so many parts to it. Stat 201, Chapter 14. Homework. Question 4. Here we go. Let's do it.
Okay. New question. Who dis? The real one. My favorite question. What are we going to do first? Tips or quantitative? We've already established that. What's the first thing we're going to do right here? First thing we do with all of these, you get a question like this, you see it, you're going to do what? What are we going to do right here? Great job. We're already going to start marking that notation. You get it right there. You got it.
Notation, brother.
Know your notation. Start by marking all your notation. Mark all your notation. So we see right here, a waiter believes that the distribution of her tips has a model, waitress, excuse me, has distribution of tips that is slightly skewed. That's not going to come into play in this question, but that means towards the large enough n condition. 40, is 40 large enough? It's not part of this question, but is 40 large enough? Is 40 large enough? Is 40 large enough? It is, because it's more than 25. So the third condition is not success failure. No one said it, but success failure is for categorical data. This one's quantitative. So this right here would be large enough such that the distribution of the sample mean is nearly normal. And that is the large enough n condition right here. So make sure to know these conditions. The third condition is large enough right there. Next, we have the mean. Well, what is that in notation? Before I stop, before I do it. It says their mean is this. So what is that in notation? What is that in notation? It is mu. And so now we could say what we expect for them to get. So we now know if they wait on 40 tables, they should expect to get about $8.10 on average from the 40 tables. Like if they were to say, oh, let's say I made $400 on these 40 tables. What was their average tip? Get some energy right there. G Fuel just did a thing with one of my favorite video games. And I'm like, I don't think we can get sponsored by G Fuel. I don't think I'm allowed to like take sponsorships. Be the first university instructor sponsored by G Fuel. They're overpriced anyways. I haven't bought any. Maybe I should try and then I'll see if they're overpriced, right? So ooh, some iced coffee. Dunkin' iced coffee sounds good. So what? G Fuel, ooh. We're sponsored by Raid Shadow Legends. Get your free Stat 201 Mubot character in Raid Shadow Legends. We're not sponsored by that. I'm kidding. Please don't. Your call. So what else are we missing notation-wise? Brian's getting back serious right here. What else are we missing notation-wise? What else are we missing notation-wise? I can't take sponsorships. What else are we missing notation-wise? Yeah, 2.5 off. That's horrible. Sigma. Sigma is the deviation, standard deviation of the original population. So with this right here, now you should probably do what? Before doing any work right here, you should probably do what? Before doing any work, you should probably do what? Before doing any work, you should probably do what? Before doing, like, I have this right here. Find your standard deviation of y bar. Exactly. So let's go right here. And 6.40 over square root of 40. Well, this one is just And so what is that going to be? What is the standard deviation of the sample mean? 40 square root 6.40 divided by... Oh, it's basically 1. Ooh, that's nice. 1.01. Okay. There's the variation in it. That is the variation in it. So with this, I'm changing the question, but just think about this. This weekend, if you've waited tables, you're going to wait on 40 tables. Now, to go on vacation, you need to make $400 this week. And your friend says, I need you to give me $400 by the end of the week. And you say, I don't have any money right now. You need to make $400 on your 40 tables. How much money do you need to make on each table to make $400 on average? Like, what is the average tip you would need to make $400 on 40 tables? I know it's not the problem, but just think that one through. You have 40 tables this weekend. Your average tip needs to be at least $10. So if we want to make $350 total, then what would we need to average on 40 tables? So solve this one for me. So if we want to make $350, what would we need to average on 40 tables? Our sample mean would need to be equal to, great job right there, yep. And so this right here is the sample mean, which I think is 8.75, is that right? We need to make $8.75 per table. Now, what's really cool about this is you could actually notice right now, what do you notice about this value, and this value? If you're doing really well at these and learning this chapter, if you've got, you say, this sample mean right here that we see, that sample mean is what to the expected mean? What do you notice about it immediately? Which I'm going to take a guess at the value of it here in a second. What do you notice? It's within Ali 5,000 points again, so it's not going to be that unusual, right? So Ali just figured out it's within one standard deviation. We're going to need some David M. Lane help here in a second. Ali, 5,000 points. You're seeing exactly what I'm seeing about that observation. So, hey, that means it's possible, right? If you need this much money to go on vacation, you might have that happen. So here is the z-score of it. So the z-score of it is going to be the following value. There's the difference, the sample mean minus the expected mean over the standard deviation. And that's going to be very close to 4 decimals. If I get this right, there'd better be a parade in Knoxville. If I were to get that right, there just should have... No, it's got to be a little bit more. Okay. That's a guess. That's a guess right there. That was just a guess, but I think it's pretty close. So what we want to do now is we need to go to the David M. Lane applet. So we have to go over to the David M. Lane applet to find out the exact probability of this, because how will this distribution look? This distribution will look how? How will this distribution look? Oh, wait. What? Open a new tab. Oh, it's opening over there. How will this distribution look because it met the criteria? The distribution should look how? It'll look normal. Correct. If you meet the 3 conditions, the distribution looks normal. Random, 10%, and also large N of n. So now we go right here and we put in our mean. Remember from our question that the mean of the distribution is equal to 8.10. That's the mean. 8.10 right here. And the standard deviation is that value right here. I'm going to put it into all the decimals. Now we want to find out that we make at least 8.75. And the answer is 26.03. So, man, so close. That was my guess. As long as we carried all the decimals, and I don't like that it says 4 decimals, because that means, how did they carry decimals? There we go, should get it right. It says we are right. So my guess was 25.6. It's because I know the z-score for the interquartile range, and I saw it was close to that, and I thought actually it's a little bit lower. So I was doing some of the calculations in my head. So I thought about 25.6%, and I'm able to do that by knowledge of z-scores in my head. But you want to go over to the applet. Let me show you again what to put into the applet. In the applet, you need to put right here the what of your distribution. Look what it says. In the applet right there, you need to put the what of your distribution. In the applet right there, you need to put in the what of the distribution. We got all the numbers on the screen right here that we're using. the mean of the distribution. There's the mean. So you're putting in this value right here, which is mu right there. In the value right here, you put in the standard deviation. And watch earlier where we've solved. Well, there's the solve for it for the standard deviation. I put in all the decimals. Just tell me if it's off by the tiniest bit. I'll give you your points back. I'm safe and put in all the decimals and then get mad at my person if it doesn't tell me I'm right. Next but not least, we had to calculate the y bar, the sample mean, and put that right here to see we make at least that. And this would be the probability of making at least this. We could also find the z-score. The z-score is close to about 0.67 or 0.66, very close to that. So the z-score would be 8.75 minus 8.10 divided by, and it's 0.64. And you could have also done this on the normal curve with the z-score, and you would get the same answer. So if you did it by finding the z-score, you could have also found the z-score and then put it on the standard normal curve. Those are the ways to solve this question. Have people gotten this question right? Is there any questions before I do the next part of this question? Is there any questions before I do the next part of this question? Any questions? So you could z-score it, but then you use the standard normal curve. I'm crushing this homework. You got it right there. Difficult questions so far. The next part's not as bad because on the next part, you want to go over to the second button on the applet. On the second button on the applet, we want to put back in our mean and standard deviation. So remember where the mean and standard deviation we found? The mean is 8.10. Now I'm going to go ahead and solve again for the standard deviation to make sure I have all the decimals. Standard deviation is 6.40 over square root of 40. So let's go right here and solve for the standard deviation again with all the decimals. Square root of 40, 6.40 divided by square root of 40, and there's all the decimals. Now, what it asks right here is it asks for the best 5% of weekends. The best, how do you get the above a value initially? Because they want to make at least this, greater than $350. Does that make sense, Ria? They want to make greater than $350. So this is the probability of making greater than that. And we found out the average tip for 350 was 8.75. So you have to find out the average tip for that. And then we want to see you make at least that. So the average tip right here was the Y bar that we found. Good questions, Ria. And now we want to know the best 5% of weekends. So you enter, well, that is going to be the Y bar. And so what that value is will be what you want to see above. That is correct. So you would divide by this amount divided by the 40 is the average you would need to achieve to have at least 350. That is correct right there. Does that make sense, Ria? Because you have $350 you want to make on 40 tables. So the average tip would be $8.75 to achieve that if you did that. Yeah. So think about that right there. To achieve that, you would need to average $8.75 on a table. So this wants the best 5% of weekends, the best 5%. And to do the best 5% of weekends, you have to have the second button clicked and you have to put in 5%. What does this mean? This is where people enter in this value, but this value is your what on the best 5% of weekends on 40 tables. This is your what on the best 5% of weekends. This is your what tip on the best 5% of weekends on 40 tables. That would be your what tip, because this is the distribution of the sample mean. So that would be your what tip on 40 tables over a weekend. That'd be your what tips on 40 tables. Is that your total tips? Is that your total tips down there? You made $9.76 on a weekend? Oof. Is that your total tips? Since this is the distribution of the sample mean, that is your what tip. That's the highest 5%, and that's your what tip, though. So that's like if it's your mean. So how would you find out how much money you made if that's what would be the highest 5% of weekends on 40 tables? That's the mean tip on the highest 5% of weekends. What would you do to turn this back into how much money you made? To turn it into how much money you made, because that's your average tips, you times by the 40 tables. Great job, Kenneth, right there. Exactly. And there it is. Just times it by 40. And that value right there should be it. We've carried all our decimals and we did it. Tough questions. One of my absolute favorites. Can I exit out of the homework? And yep. Still keep your spot. And great job, Corinne, right there. You can exit out, still keep your spot. Really good if you have time to go over the Canvas content. Yeah, I'll do the Canvas content at the end of this. You got it, Ethan. Thank you so much, Ethan, for asking. Really tough question. Really good one right there. So a lot of steps. Which of the, let me put the note in here. Oof, hardest question done. Woo. We catch a ton of Pokemon tonight. Set to a 1. You know, like, daylight savings happens, and I'm just like, oh, now I can stay up an extra hour playing video games. Should have got more sleep. Have fun, Tara. Thank you so much for being here. Which of the following is not a condition to check to estimate the mean of a population? This should jump out to us immediately. We talked about this a lot today. Absolutely love this question. Immediately, you should know the answer to this. Which one is it? When we do it right here, if we are doing the mean, which of these do we not check? You ready? Condition 1. What is condition 1 for checking the mean of the population or doing the sampling distribution of the sample mean? Kind of got right. The first condition is random. The second condition is less than 10%. So we want the data to be gathered randomly. And then we have less than 10%. So they literally condition 1, condition 2 right here. And then the third condition for quantitative data is going to be the large enough n, which they're alluding to right here. The data comes from population. Yeah, but large enough n right there, basically. The way they word that should be worded a little bit better. But success failure is only for what kind of data? Success failure is only for, it's a great question. Success failure is only for what kind of data? Success failure is only for what kind of data? Categorical. Make sure to know that when you get to the third condition, pause and make sure you know success failure is only for the sample size condition for a procedure with categorical, not exactly. Yep. And the next one says, this is a theoretical one, so that one's super quick. Nice job. We're almost done with the quiz right here. And so 53, 23, stat 201. Chapter. We did this one earlier, but it's a good one. Okay. So this one right here says that it's a different one. A study at the annual compensation for 800 CEOs, so I looked at the annual compensation, for which the true mean and standard deviation were this and this. So what values did it just give you? What values did it just give you? What values did it just give you? What values do we know right now? Let's go bring it over to him. And it's quantitative, so we use this one. And we're going to do different sample sizes, right, Kenneth? That's what they're doing. So it just gave us mu and sigma. Great job, Sullivan, right there. It just gave us mu and sigma. And mu. And sigma. And then we do different sample sizes. There you go. So what will be the same for all these answers? What will be the same for all these answers? And look, technically lowercase n, that is correct, because capital N is population size. So what will be the same for all these answers? When you solve this for the theoretical answers of what the mean should be for all of these, what will be the same? The mean will be the same, because the formula for the mean is literally just the mean of, or the expected sample mean is equal to the mean. So mu y bar is equal to mu, and there's mu. So we can just go right here to all these questions and put in, well, I'd expect from 30 to see a sample mean of, where is that? 10, 7, 33.74. And now the standard deviation is just going to be what? Every time we solve a standard deviation right here, what is going to change as I solve this multiple times? And so I color code to help this out right here. What is going to change as I solve this? As I solve this, we're just going to change what the sample size is. So the standard deviation will get smaller. So we just take the 18753.66. Let's take that right here. Well, we got, oh my gosh, R is opening up. Go away, R. Okay, so here it goes. Watch the steps right here. Standard deviation gets smaller as n gets larger. Exactly. And that's the central limit theorem. One of the things it says is there's less variability in the sampling distribution as the sample size gets larger. It also becomes more normal due to large enough n. At some point, it's basically a normal distribution. Basically a normal, if the n is large enough. Great work right there, Kenneth. We got to throw you some more points. Great job reviewing these questions and answers. Remember, it's all about just practice and repeating things back just like that. Kenneth, great job. You know what? We got to give you the big points. Thank you, everyone, for being here. It's the practice that makes us understand it a little bit better each time. So 30 square root 18753.66 divided by that. Oh my gosh. Ay, ay, ay. 2 decimals. Oh, this one's fun. I just like dividing numbers all the time. Okay, so now 18.5. You know what's going to happen. That, like, literally as I say it. What is someone predicting will happen right here? If you are close enough, just tell me. That's 10. Oh, blessings. We're good. 1875. I should do it in the calculator. 0.37. Right? 18,753.66 divided by 10. 81857. There we go. We get formula. Yep, you get the formula sheet. Review 2. Review 2 is where the formula sheet is at. Here, we'll show it right here. Check out, and I've been using the formula sheet all today, so check it out. 200. I used to know square root of 200. Oh, because it's like 2, but the decimals moved. That's like square root of 2, right? No ways that look that's. I just want to see this. It is. Oh, because you could take and factor it down to 200 is 2 times 100, and then square root of 100 is 10, and square root of 2 is that. And yeah, wow, okay. I love math. Math is neat. There we go. All right, so let's take that, divide 18753.66. And did we do all the maths correctly? Does Brian still loves maths? We do loves maths. So this was what I was doing right here. I was just changing what the value of n was. Does that make sense to everybody who's solving this right now? Just plugging in different values of n. The mean is still the mean for all of them. You would still expect to see the same sample mean from a sample, regardless of sample size. But the thing that changes throughout this problem is going to be the standard deviation getting smaller by a factor of square root of n. So there's going to be less variability in the larger samples. A lot of questions have kind of highlighted that theme about the central limit theorem. Great work right there, Corinne, and thank you. Please let me know if anyone has any questions. Those are the formulas used to solve this question right here. How close are the theoretical values? I don't even need to look at them because the theoretical values are going to be reasonably close to, both of them are going to be reasonably close. Just to show you after we get the answers right, well, that was the question. The question right here shows you what they should theoretically be. Right here's the theoretical and here's the simulation. So you could kind of use these a little bit to check, like your numbers aren't going to be super duper close, but they're going to be reasonably close. Just say, what did we see in a sample of 30? What did we see in a sample of 50? And we'll see something close to the theoretical mean and close to theoretical standard deviation in simulations of it. So you could use those to kind of do a check. Please make sure to be, like, if you get it wrong, don't get them all wrong. Don't go in here and just guess and be like, Brian, that was close. Because you could, well, the answer to the mean is obviously that one. How perfect should your answer be for the left column? How many decimal errors should you have? Because this is the easy one. That's the easy formula. How perfect should your answers be for what is the mean for the sampling distribution of the sample mean? What is the mean for the sampling distribution of the sample mean? How perfect should your answers be for the left one? Because that's the easy one. The left one, you should get these right. You shouldn't, this is just theoretically what we saw in a simulation. I shouldn't say theoretical simulation, it's just a simulation. So the simulation right there is going to be close to the theoretical values, but gets into a lot about how simulations work and increasing law of large numbers. More simulation will go towards the true values. This didn't run their simulation long enough. Last homework question. Let's knock it out. Let's do it. Here we go with the last homework question. 1.00. Stat 201, Chapter 14, Homework Question 7. Okay. The histogram to the right shows annual compensation rates in thousands of dollars of chief executive officers, CEOs of large companies of the 800. The average compensation was in thousands of dollars. Is this? It's a lot. It's to the left skew. Oh, it is left skewed, right? Oh, is there just asking which way is it skewed? Oh, yeah, it's left skewed. If you're wondering how we know left and right skewed, we know our Monster Man. Monster Man is right to the high, left to the low, whatever way the Monster Man's tail goes. So if the Monster Man's tail goes to the low side, And there's Mr. Monster Man, got his Monster Man tooth, his Monster Man eye. Monster Man's tail is left skew, so Monster Man right there is skewed to the low side. Right to the high, left to the low, whatever way the Monster Man's tail goes. That's the way we figure it out. Good saying right there. Okay. Explain how these histograms of the simulated values demonstrate the central limit theorem. So as n increases, the distribution of the sample mean will become more what? As n increases, the distribution of the sample mean will become more what? As n increases, the distribution of the sample mean will become more normal. So let's see if their graphs show this. Right here is at 30, 50, 100, and 200. Oh, see, they're going for a... See how there's still a tiny bit of skew, but here there's a little bit? So they're saying that's ridiculously skewed. They're probably going for 200 with the way this looks. Even though we say 100 is pretty enough, good enough for everything, I think they're going for 200 being enough. That's what I'm seeing here visually. I would give it to you if you put 100. You'd get the points. The simulations support what the central limit theorem says about the sampling distribution of the sample models, the means. Oh my gosh. The simulations support what the central limit theorem says about the sampling distribution model for the sample means because as the sample size increases, the peak of the histogram, where's the peak of the histogram? The peak of the histogram should be close to the what of the distribution. The peak of the histogram should be close to the what? The peak of the histogram should be close to the what? Should be close to the mean. So do you see it's about at 1600, about at 1600, about a little above 1600, a little above 1600? At all points, the peak is a little above 1600. Do you see right here? Little above 1600, little above 1600, little above 1600, little above 1600. So the mean is doing what right here? And the answer is right here. The mean is doing what? As the sample size increases, the mean is doing what? Don't look at their answers yet. The mean is doing what mathematically right there, and visually it's doing what? The mean is doing what? As sample size increases, and look at the equation, the mean does what? As sample size increases, it's staying the same. Because there's nothing in the... We're solving for the quantity on the left, and so this is the mean, and it's going to be the mean of the sampling distribution. So it's staying the same. It's not changing. It stays about the same spot. So the mean is staying about the same. That's where the peak is at, the mean. The shape of the distribution is becoming more what? So as n increases, the shape of the distribution from left skew to whatever that is becoming more what? Don't look at their answers, practice. The shape of the distribution is becoming more what? Becoming more normal, which the central limit theorem says, great work right there, becomes more normal. And the variability is getting water, which goes towards the sample size increasing. As sample size increases, variability does what? As sample size increases, variability does what? Variability decreases, which is the second part of the central limit theorem, which says the sampling distribution will have a smaller standard deviation when n increases, exactly, because we're dividing by square root of n. So that is the variability, which is standard deviation, and the variability decreases right there, and that has got it. I don't think did we miss one? Oh, wait, one more thing? Oh, my gosh. Comment on the rule of thumb that with a sample size of at least 30, the sampling distribution sample mean is normal. No. Since the distribution of means for this simulated samples of each size is no. Since the distribution of means for the simulated samples of any size remains skewed, the rule of thumb does not hold for highly skewed distributions. That sounds about right. Since the distribution of means for the simulation samples become no. Since the distribution of means for the simulated samples of any size remains skewed, they're kind of going towards an F distribution. Between two answers. Since the distribution of means for the simulated they're saying it is normal. They better not go with this. With a sample size of at least 30, the sample distribution of the mean is normal. No. They're trying to show you, because here's 30. You can just look at it visually. It's not normal. So they're trying to show you that at times you might need a very large what? At times you might need a very large what? At times you may need a very large what? large N. Because, and I hate that these 30, it's like what size exactly do you need? Like the more skewed it is, the wider N needs to be. Exactly, it's super skewed. It's like super duper skewed. It's the super duper skewed. So you need like 500 or something. So like the more skewed it is, the larger N needs to be. So that one's ridiculously skewed. So N needs to be very, very large. So and they're showing you via simulations. So on the people say, well, how do you test this on the test? We might just literally tell you it's a little bit skewed, or we might say it's normal. If it's normal and we sample 10, is 10 large enough? If it's normal and we sample 10, is 10 large enough? And this is the way to check it. So if it is normal, I've just told you it's normal, then is 10 large enough? Yes or no? Is 10 large enough if it's normal? Is 10 large enough? If the original distribution is normal, is 10 large enough to have a to meet the central limit theorem? Is 10 large enough? Ah, wait. Yes. So know the shape, it's normal, right? So what is the required sample size if it's normal to meet the condition? If it's normal, the sample size needs to be at least what? If it's normal, the sample size needs to be at least what? Great job, Sullivan. Great job. You bet. It needs to be at least 1. So if I say it's 10 and it's normal, then the distribution of the sample mean will be normal. So it would look like the following way. We could show it theoretically over here. This is normal, right? So if I go and take 10 observations, the resulting distribution of the mean, if the sample size is different, how is it relatively close to mean with different sample size? So do you see where the center of this curve is at right here? Do you see the center of this curve is at 16? Does that make sense? It's at the mean. So if I were to take samples of size 10, where do you expect this blue dot, which is the mean of these observations, to land? Where do you expect the blue dot, if I'm taking from this, and this is like people's scores. Great job, Kenneth, right there. Go grab some lunch. If this is people's scores, and the average score is 16 out of 20, let's say. Don't worry, that's 32. We'll just print this out of 20. If the average is 16, then where would you expect the blue dot to land? Because the blue dot is the average of 10 dots. So where do you expect the blue dot to be? Probably pretty close to where? Where do you expect the blue dot to be? Where would you expect it to be? What is the expected sample mean of this? So the expected sample mean is 16, and you're actually doing the formula right here. Because if you know the true mean is 16, then you would expect a sample mean to be 16. So you know the truth is 16, so if I do an observation down here, you would expect it to be close to 16. But there's also going to be what? Variability in this answer. And look down here, the variability is the standard deviation. How is this 1.58 found? How is this 1.58 value found? How can you mathematically get from the original standard deviation the new standard deviation down here? And look how this is normal, because this one was normal. This is also normal. It just gets more normal for larger sample sizes. So how could you get this 1.58 from the original standard deviation for a distribution of sample size 10, which is the distribution of means of sample size 10? How could you get this 1.58? How would this value down here be obtained? So to get 1.58, take the original standard deviation of 5 and divide it by the square root of 10. And there's that 1.58 right there. Does that make sense? So 1.58 is the original standard deviation of 5 divided by the square root of 10. And we've just done the formula right here, which says the new standard deviation for the sample mean is equal to the original standard deviation over the square root of n. And so that's what we're solving for down here. Does that make sense to everybody? This is what we're doing right here, is we're talking about the distribution of sample means of size 10. You're welcome, Ethan. Good questions. These are tough. It's kind of like chapter 5, but it's kind of different. And I think we've probably done most of the quiz questions. I think, let's see right here. Let's go to Spice. There we go. Have we done most of the quiz questions? Oh my god. Trying to wake up. Gotta wake up. Trying to see. Trying to wake up. Take a look, see these quiz questions. Let's see. We did the salmon question. We did the scores question. We did the waiter waitress. There's a grocery store one that's very similar. And we did waist sizes earlier. Should we do Canvas content to end? Because I think we did all these. They're very similar. The ones we didn't do are literally almost identical to the ones we have done. So the homework basically does it all. We basically did all the homework, and they're all very similar, Ben. Do you want to do Canvas content, finish off with that? If we do Canvas content, we've pretty much done everything related to this chapter, and let's see if we can just destroy the Canvas content. Yup. Let's knock out Canvas content. Let's finish off here with Canvas content today. Okay. Canvas content. Number 7. We just did all the homework. Did you get 100? You got the hundreds? Let me know. That's awesome. You can or not. Let me know if you want. Let's go check it out. First question on the quiz right here says the success failure condition states that your measurement must be either a binary. What does the success failure condition say? Don't worry about this question. Just tell me what the success failure condition says. Put it in your own words. Be like, the success failure condition says what? So what does the success failure condition say? It says you need what? Someone says, what is the success failure condition? How would you describe it to them? How would you describe it? What does it say that we need or don't need? Is that a proper way to talk about it? What does the success failure condition say? The success failure condition says close, Ben, close. We need that NP and NQ, which this is NQ right here, both NP and NQ, when you solve them out mathematically, have to be greater than or equal to 10. So let me ask you this. Are you ready? If 45% of UT is from Tennessee and you talk to 200 students, how many of them would you expect to be from Tennessee? If 45% of UT is from Tennessee and you talk to 200 students, how many would you expect to be from Tennessee in your sample of 200? How many would you expect? Well, be careful. Remember, we're talking to 200 students. So 45% are born in Tennessee, which is the true proportion apparently. So it's true that 45% of students are born in Tennessee. So then solve the equation right here, NP. And so if it's true 45% are born in Tennessee and you talk to 200, how many would you expect in your sample? 90. Does that make sense? So you'd expect 90 out of the 200. So that's at least 10. How many would you expect to not be born in Tennessee? So solve the mathematics here on how many you would expect to not be born in Tennessee. And what do you notice about NP and Q? 110. And notice that the how many you expect to be born in Tennessee and how many you expect to not be born in Tennessee adds up to 200. And both of those quantities were greater than or equal to 10. You must have at least 10 successes, at least 10 failures. So is this a proper way to describe the success failure condition up here? Does that say everything we just talked about? True or false? Does that description right there say everything we just talked about? Oh, and P is 0.45 and P, so I'm gonna put this in the chat, Meredith. P is equal to 0.45, N was equal to 200, and P is equal to 90, which is the amount of successes. And Q is equal to 0.55. And P and Q, since their probabilities, must always be contained between what and what. Whenever you're finding P and Q for any of your notation, P and Q must always be between what and what. The values of P and Q must always, because they're probabilities, the values of P and Q must always be between what and great. Great job right there, Ben, on the N and Q. And we got to throw some 5,000 points. Good practice here, Meredith. Anytime if you say P is this and Q is this, they must be between what? So the answer is false previous one. And P and Q must be between what and what? If you're going to write down what P is and Q is, they must be between what and what? So if I write down P is this, it must, since it's a probability and a rule of probability states they must be contained between what and what? Since it's a probability. And so And so what should P and Q be between? If you have P written down, it must be contained within what? And it's a proportion also, so we usually do it as a decimal. So P and Q must be between 0 and 1. Does that make sense? P and Q have to be between 0 and 1. So you can't go outside 0 and 1 P and Q. So that's a good way to look at it and be like, okay, wait a minute. P has to be a proportion. Exactly, Meredith. Great work right there. P and Q are between 0 and 1. And then NP and Q are the amount of successes, the amount of failures we expect. So that is the amount. This would be false. That is correct because it deals with at least 10 successes, at least 10 failures. This one right here is going to be all about that notation. So let's write down the notation for this question and see if we can get it. For this question, it says, and I prefer to interpret it this way, the defect rate is this. Let's just say the defect rate is this, and now I've just told you what quantity. If this is the defect rate, which defects are categorical, so if that is the defect rate, I've just told you what quantity. If that is the defect rate, I've just told you what quantity. If that is the defect rate, the proportion of defects, I've just told you what quantity. So if that is the defect rate, I've just told you what quantity. If that is the defect rate, what have I just told you? Not mu. Good guess right there. Not mu. So defects are categorical, right? Good guess, Lachey, right there. I'll throw some points. Defects are categorical, right? Like, is something a defect? Is it not defective? Is it defect? Is it not defect? So going over here, if I say the proportion of defects is this, I've just told you what? Because defects is categorical. So always first identify categorical quantitative. So what have I told you? What value? What notation value have I told you? What a notation value have I told you? Not p hat. Good guess. Not p hat. P hat would be sample proportion. N is sample size. So the true proportion, if we say the defect rate is this, that would be, if I say this is the defect rate, we know it is this. The defect rate is this. That would be, only a few more things up there to choose from. If we say that is the defect rate, it's the true proportion. It'd be P, true proportion of defects. Great job right there, Ben. We'll throw you some points. It is the defect rate right there. That would be, this is the defect rate. So that is P for true proportion right there. And as soon as you find P, what do you find next? As soon as you find P, you instantaneously find what? As soon as you find P, you instantaneously find what value? You should just be like, boom. Yep. How do you find Q? How do you find Q? I found it right there. How did I find it? Like that. So we have proportion of defects, proportion of not defects. Yep. And then when you hear success failure, what are you going to check mathematically? When you hear success failure, what do you need to check mathematically? So we've got the hints on the screen. What do you need to check mathematically right over here? What do you need to check? What do you need to check? What should you check for success failure? So remember, success failure is only for categorical. When you hear success failure, you want to check that NP and NQ are both greater than or equal to 10. So what are we missing to check this? What value are we missing? And then we'll be able to solve this question. Kind of. And that's what we need to go find, right? Right, Ethan? So we need to find N. What is N? What is the quantity of N? What quantity is N? Where is N? What value is N? N is sample size. N is 500. Yep. Do we meet the success failure condition? Yes or no? Do we have at least 10 successes, at least 10 failures? Do we meet the success failure condition? Yes or no? Yes, we do. We do meet it. We have at least 10 successes, at least 10 failures. We have met the success failure condition. That is, we have more than enough information. You bet we do. The 3 conditions for sampling distribution must be met in order to calculate p hat. How do we calculate p hat? Oh, no worries, Lindsay. Awesome work. We're going to end here soon. We just did all the homework, so check it out. I'll post the links here soon after. We just did all the homework. How do we calculate p hat? P hat stands for sample proportion. How do we calculate p hat? How do we calculate p hat? How do we calculate p hat? Anyone know how to calculate p hat? How do we calculate that? P hat is calculated how? Like, if I went out and talked to 50 students and 20 of them have taken Stat 201, what would p hat be? So knowing the notation here is key. So I went out and talked to 20 students. Well, 50. I said 50 to start. And 20 of them have taken Stat 201. What is p hat? What is the sample proportion of students who have taken Stat 201? So I talked to 50 students and 20 have taken Stat 201. So what is p hat? P hat stands for sample proportion. Like that. That's sample proportion, the proportion in your sample that meets the criteria you're interested in. So what would this be? What would p hat be right here? Oh, well, p hat doesn't, so mu p hat, which is the expected mean of the sampling distribution for p hat, is equal to p. So that's not the same as p hat, though. P hat is a sample proportion. So this would be Brian went out and spoke to 50 students. 20 of them have taken Stat 201. What is the sample proportion? Brian went out and spoke to 50 students, and 20 have taken Stat 201. So what would the sample proportion be? So just pretend, don't do any high-level statistics. I talked to 50 students, and 20 have taken Stat 201. What is the sample proportion? Now, if it's a proportion, the answer must be between what and what. So if it is a proportion, the answer must be between what and what, just like how proportions work. So the proportion of students who take Stat 201, since proportions are like probability, it must be between what and what. P hat has bounds on it. P hat must be contained within what? 0 and 1. Great job, Lachey, right there. You're right. So we know some bounds for the answer. Great job. We're throwing some points, Lachey, earning everyone another 5,000. Keep those answers up. What is 20? Remember, it comes down to the notation. 20 is how many students took Stat 201. So what is 20 in notation? Great job, Meredith. Meredith, you got it right. That is, you found p hat. That is p hat. So p hat is 0.4. That is correct. So what is 20 in notation? So what is 20 in notation, though? 20 is the value of x. X being the number of successes. 50 is the sample size. Does that make sense? So p hat is the sample proportion, which is the number of successes out of your sample. So when you think of sample proportion, it's the percent or the proportion of successes out of your sample p hat. That's different from mu p hat, which is the expected sample proportion. So this says expected sample proportion is the true proportion. Basically, if I take a sample, I'd expect to see this, but which is that I expect to see that. So my expected sample proportion is the truth, which is different. There's 20 successes, X being successes. Exactly. Good practice right there. So did I check any conditions? Yes or no? Did Brian check any conditions? Did Brian check any conditions right here? Did I check any conditions? Did you hear me talk about conditions? Did I talk anything about conditions with this? Did I give you a whole speech about conditions? All the work we just did on the screen, anything about conditions? Don't worry. Don't worry. Take a shot. Did you hear me talk about conditions? No, I didn't talk about conditions. Because the conditions are what we need to check to see if what. The conditions are what we need to check to see if what. When we check the conditions, this applies to thinking about the what. When we're checking the conditions, we can calculate the mean or different things. Checking the conditions is all about seeing if the distribution is normal. So it's when we're doing this, is mu also p hat? No, mu p hat is a phrase. Good question right there, Ben. Mu p hat is the phrase, the mean or the expected value for the sample proportion. So the way this would work is if I tell you that, let's say the truth is that 36% of UT has taken Stat 201. If you took a sample, what would you expect to see? If the truth is that 36% of UT has taken Stat 201, if you took a sample, what would you expect to see? If it's true that 36% of UT has taken Stat 201 and you took a sample, what would you expect to see? So if it's true that 36, I'm saying like we know from data that 36% of UT has taken Stat 201. What would you expect to see in your sample? You'd expect to see around 36%. Does that make sense? So mu p hat is the phrase expected sample proportion. It's not your sample proportion, it's what you would expect. So you saw something that was a little bit higher. Does that make sense? What you saw in your sample of 50 students was a little bit higher. You could also go and calculate the standard deviation by doing p times q over n square root, and that is equal to the standard deviation of p hat. And so that value right here is going to be 0.4 times 0.6 over square root. And we know because q, oh, no. Gosh. I used p hat. Does someone call that out? The answer is false right here. That is correct. Notation. And so the standard deviation is going to be 0.36 times 0.64 divided by square root of 50. There we go. 0.067. There we go. And the mu p hat is equal to 0.36. And look at the value we saw right here. The value we saw is what? Who can finish my sentence as I solve the mathematics right here? The value we saw, here's the math over here on the bottom, our p hat of 0.40, subtract the expected mean, divide by the standard deviation. Our value is what? And how we're doing the z-score, that's right. And what do you notice about the z-score if you look at this as I solve it right here? The z-score is what? It's less than what? Not if I do that. It's less than 1 standard deviation. So this is not that unusual. It's less than 1 standard deviation. So what we saw in our sample was not that unusual given the truth. And so we would say this was not that unusual. Great job, Lindsay, right there, and good practice. So you would say what I saw in my sample was not that unusual. I expected to see about 36%. I saw 40%. We should have a variation. Where's the variation right there? So that's kind of a review of this chapter. And the answer is no, you don't calculate p hat. It's just x over n. There's no requirements. The sampling distribution of the sample mean will always have the same what. So what, and both of these always have the same what. What is always the same for the sampling distributions, regardless of sample size? It's always the same what. So look at the equation sheet right here. The sampling distribution for the proportion or the mean, either one will always have the same what value. It's very easy to solve this. If you say the average guy at UT is 5'9", you talk to 20 guys, what would you expect the average height to be? 5'9". We're talking about the what. The sampling distribution will always have the same what as the original parent population, the data it comes from. So think about this. The average score on the Stat 201 exam is a 75. If you talk to 10 people, what would you expect their average score to be? The sampling distribution will always have the same what. The standard deviation actually gets smaller. So the things that change about it, good answers right there, good try. Let me throw you some points here in a second. The standard deviation actually gets smaller as n increases. So the standard deviation will get smaller as n increases, and it becomes more normal, which is the shape. Does that make sense, Lindsay? So the two things that change are right here. that the sampling distribution will have a smaller standard deviation as n increases, and the mean stays the same. So the mean is staying the same, but the shape of it will become more normal. So as the sampling distribution will be more normal as n increases, so the shape becomes more normal. So the shape will change. So as the standard deviation gets, or as the sample size gets bigger, then it's going to have a different shape. It's going to have a smaller standard deviation, but the mean stays the same. And we just see that here with the formulas, where if you notice right here, I'll highlight just that. The formulas for the mean are independent of sample size. It's going to be that the mean of the distribution of the sample proportion is equal to the proportion. The mean for the distribution of the sample mean is equal to the mean, and those stay the same. The central limit theorem relates to which of the following conditions? I tried to make this really clear today. Which of the following conditions relates to the central limit theorem? The central limit theorem relates to which of the following conditions? Which of the following conditions right here relates to the central limit theorem? So I tried to drop, I saw that one when we were working on it, so I tried to make that super clear. I tried to drop some hints for the questions right there. So the central limit theorem is all about it being what? Boop. Great, nearly normal, yep. Right there, the nearly normal, we check it with the third condition for proportions or for quantitative. The nearly normal right there. And that's got it. We should get another 10 out of 10. So good work. And if you're wondering, we did 2 other versions of this earlier. So if we didn't get to your question, check out the earlier office hours. But I've got such great news. We have done all the homework for chapter 14 today. We did all the Canvas content. And I'm going to grab some lunch here. We've been going for an hour and a half. But who got 100 on Canvas content? Anyone get 100 on the Canvas content, 100 on the homework? Who got some hundreds? Give shout-outs right here. We'll end off right here with a little bit of music. I've already ordered my music. Got to figure out where things are at. But I'm excited. Let me drop the notes in on this. Let me drop the notes so people can access this pretty quickly. I have 2 on Canvas content that you didn't have. Which ones do you have, Ben? Check out earlier today. I'm going to go put the notes in for the classes. Did you do the other central limit theorem question I couldn't find? What does it say, Caden? Let me know what it says, Caden. Say, Caden. Oh, there's Brian talking in the background. What does it say? The conditions for sample distribution sample mean when you know the true mean are. What are the conditions? Condition 1. What is condition 1? What is condition 1? The question on which the following happens. So which of the following will happen to the distribution of the sample mean as the sample size increases? Condition 1 is random. Condition 2 is 10%. And then condition 3. Condition 3 is what? This is sampling distribution of sample mean, right? Condition 3 is going to be the large enough n. Yep. If we're doing quantitative, that is correct. If we're doing categorical, then it's going to be success failure up here. So categorical success failure. Condition 1 is always random, 10%, but success failure is for categorical data. Which of the following will happen? So what happens to distributions right there, Caden? What happens to the mean as n gets larger? So what happens to the mean as n gets larger? And we'll look at Ethan's. Oh, sorry. Who got hit by something? No, I think Mubus just being crazy. The mean stays the same. What happens to the standard deviation as n increases? What happens to the standard deviation for both of these as n increases? The standard deviation gets water. The standard deviation gets water. As n increases, the standard deviation will get water. Well, and the shape gets more normal. The shape gets more normal. The standard deviation gets smaller. So the standard deviation will get smaller as n increases, and then the shape of it becomes more normal, which is in the central limit theorem notes that we talked about over here, that the shape becomes more normal. The sampling distribution will be more normal as n increases. The sampling distribution will have a smaller standard deviation, and the mean stays the same. So this is the mean staying the same. My last on Canvas says the 10% condition states that we need to sample more than... so what does the 10% condition say? The 10% condition says we need to sample what? Do we need to sample more than 10% or less than 10%? The 10% condition says what? Less than 10%. Good job right there, Ethan. Let's throw Ethan on as a mod right here. Thank you, Ethan, for staying here and doing the work. I hope you got that 10 out of 10, Ethan. Everyone, you can announce it if you want. It's your call. But I love hearing those. Got that 10 out of 10. And remember, practice. Do your second attempt if you have a second attempt to practice. It's really good. I'm gonna put the notes in because we got the test coming right up. You're welcome, Ethan. Great job right there. Get those 10 out of 10s. Morning office hours already getting watched a good bit. We're dropping in. We did more Canvas content earlier this morning. You're welcome. Great job, Lachey, right there. And last few. You're welcome, Meredith. Thank you so much, everybody. A little chill music to end right here. Chill music. Okay. You're welcome, Ben. You're welcome, Meredith. I saw it still on the screen. Awesome. We've got all the notes in for classes. Looks like people got those 10 out of 10s. We love seeing that. Well, with that, I'm going to go take a break. Got a meeting coming up here soon. But keep up the great work. My hair's just going to keep falling. Just gets longer and longer. Bye for now, everyone. There's the notes in the video.